Hey everybody, it's Friday, January 15th, and as you can see here in the aim today, our goal for today's video is to talk about how energy flows through a system. Now, I think it's pretty apparent from some of the answers that a lot of you gave for the problems on the sheet from yesterday, or I guess the sheet that you answered on Wednesday, that a lot of you remember a little bit about conservation of energy. And that's really the focus of today's video, to talk all about conservation of energy. Now, we are going to spend a number of days on this because it is an extremely important topic in this course, but we're going to start simple and then slowly step up the difficulty over time. Specifically, in the context of today's video, today we are only going to focus on the conservation of mechanical energy. So to understand conservation of mechanical energy, as I'm sure some of you may remember, it's first important to remember what mechanical energy is. Mechanical energy, if you remember, is the sum of potential and kinetic energies. Essentially, mechanical energy is just every kind of energy besides heat. And so, as I've written here, to put that in the form of an equation, we can say ME, the symbol for mechanical energy, is kinetic energy plus potential energy. Now, notice here I have not written this specifically for gravitational potential energy, because gravitational potential energy is not the only kind of potential energy. We are eventually going to talk about elastic potential energy, or the potential energy stored in a spring. But for now, we'll just keep this general and write kinetic plus potential. And of course, depending on the exact situation and the problem you're looking at, that may be gravitational or elastic or both. So mechanical energy is the sum of potential and kinetic energies. And what the law of conservation of mechanical energy says is the sum of the kinetic energy and potential energies before an event is equal to the sum of kinetic and potential energies after an event in a closed system. Now, we'll talk about what the closed system part means in a moment, but it's important to remember, as a mathematical statement, a conservation law in physics is very straightforward. It just says whatever you have in the beginning, that's the amount you have at the end. This is the first of a bunch of different conservation laws that we are going to discuss in this course this year. And so this obviously is an important concept to remember, that when something in physics is conserved, all we mean is that the total amount remains the same over whatever the event is that's happening in the specific problem, whether it's something being dropped, something being thrown up, something rolling down a hill, something colliding, whatever it is, the initial amount equals the final amount. Now, what is particularly unique about conservation of energy, unlike momentum, for example, is that, like, momentum is momentum, but energy can exist in many different forms. And so it's very important for these problems to remember that while the total amount of energy is going to remain the same, the type of energy can change. Of course, the process here is very simple. It's just that if a certain amount of gravitational potential energy changes into kinetic energy, the amount of kinetic energy you're going to have is just going to be the same, if the conversion is complete, at least. So as it says here, the sum of kinetic and potential energies before an event is equal to the sum of the kinetic and potential energies after an event in a closed system. Now, ordinarily, I would write this underneath here, but I can't because I've run out of room here. So you can write what I'm about to write over here directly under that in your notes. We can expand that equation out a little bit to just look like this. The initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. Exactly what that equation looks like, of course, depends on the situation posed in the problem, but this equation covers all situations in general. Take a minute to pause this video here and write that down, and when you hit play, we'll address a little bit about what we mean by a closed system. Okay, so you're always going to see this, that something is conserved in a closed system. And so it's very important that we get at exactly what that means. And so here we're going to ask a series of questions to sort of be able to figure that out together. So as we already said, conservation in physics refers to the value staying the same over the event that's happening in the problem. The big question here then is, what changes the energy of a system? We're saying here, if the energy is conserved, it's the same number. It's not changing. Well, if the energy was changing, what would make it change? The answer here is work. When work is done, energy changes. Specifically, the work-energy theorem says work is equal to the change in energy. The amount of work that happens is equal to the amount the energy changes by. So work done changes the energy when work is done on a system. Well, then we can say, well, if work is what changes the energy, then how can we use this fact to describe situations in which the energy of a system will not be conserved? And the answer here is just a simple application of the logic. If we're saying the energy is conserved, meaning it's not changing, and the thing that changes energy is work, well, then energy in these situations, there's a big note here, energy in these situations is only conserved when there is no external work done on the system. And that could be by friction or any other resistive forces like air resistance, or really any other forces in general. And so essentially, when we say the mechanical energy is conserved in a closed system, what we mean by that is mechanical energy is conserved in a system which is not experiencing any external forces which are doing any external work. When you have a system that is free of external forces that are doing external work, the energy in the system is conserved. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So the key difference between the way we are going to sort of not only just approach these problems from a mathematical standpoint, but really also the shift in thinking that we're going to have about these problems in this course compared to the way we did this in honors physics, is in this course, we really want to make sure we are being very careful about considering what in the problem is part of the system. The first thing that we should note here, even before we write down any of what's printed on this slide here, is you specifically as the problem solver, as the analyzer of the situation, you decide what the system is. Of course, what you decide to include as part of the system ultimately is going to affect the analysis. The reason why it's going to affect the analysis is because in any conservation of energy problem, it's very important to define what the system is so you can clearly define what is external and internal to the system. Since an external force will do net work on the system, but an internal force would not. That's a very important idea. So if we were saying here that, for example, we had an object, let's just say traveling on a horizontal surface, and it had a certain amount of kinetic energy, and it collided with another object, which we'll just call object B, which is just sitting there. When these objects collide, object B is going to exert a force on object A, and object A is going to exert a force on object B. The analysis changes drastically based on your choice of whether or not to include object B as part of the system. If you include object B as part of the system, then clearly when these objects collide, object A is going to exert a force on object B, and object B is going to exert a force on object A. But since both of the objects, objects A and objects B, are part of the system, those forces would be internal to the system. And if you're considering the system as a whole to be both objects, then there is no net force on the system. Because yes, one of these forces acts individually on object A and one of these forces acts individually on object B, but if you're considering the system to be both objects together, then the net force on the system is zero because they cancel each other out because they're equal and opposite forces. And so the analysis here would be pretty straightforward. Object A is going to have a certain amount of kinetic energy. When that collides with object B is going to experience a force in the direction of its motion, and so it's going to speed up and thus gain some kinetic energy. And object A, on the other hand, is going to have a force exerted on it in the opposite direction of its initial velocity, and so it is going to lose energy. And according to the law of conservation of mechanical energy, the exact amount of kinetic energy gained by object B is going to be equal to the exact amount of kinetic energy lost by object A. On the other hand, if we did not include object B as part of the system, thus we were only looking at object A would be moving along with a certain amount of kinetic energy. It would collide with object B and experience a force exerted on it from object B. And because object B is not part of the system, the work that object B does on object A would be considered external to the system. And of course, we would understand the net effect of that force instantly, because it's the same thing that just happened in the previous example. Object A is going to slow down because it experiences a force exerted on it in the opposite direction of its motion. It's going to have a decrease in kinetic energy. Essentially, the work is negative because it makes object A lose its energy. And so you would get the same result if you calculated this mathematically, but the point here is that if you consider object B part of the system, the forces that are exerted between the objects are internal to the system, and so you don't have to consider any net external work. However, if object B is not part of the system, any force that it exerts will be external to the system, and so you must consider the work that's done by object B. Now, the point of distinguishing between these two examples, I hope, is pretty clear, because the answer is going to be the same. It's just the way you think about it that's going to change. And that's the key point here. And so there is a clear difference here, but the distinction is subtle. There's work done in both situations, and that's the important thing to realize. Because in either situation, object A is going to lose energy and object B is going to gain energy. The point is, when you consider object B as part of the system, the amount of work done on object B is positive because it increases the energy of object B, whereas the work that's done on object A is negative because it decreases the energy of object A, and the total amount of work is going to be zero because the exact amount of energy change experienced by object B is going to be equal to the exact amount of energy change for object A. The gain for B is equal to the loss for A. Whereas when you consider B not part of the system, there is still work done on both objects. It's just that for the system consisting of object A just by itself, now the work that object B does is external to the system. And that's the distinction. Generally, one of the biggest challenges in solving these problems is you deciding what the system is. The main piece of advice that I'll give, at least at this point before we've solved any problems, is you want to do this in such a way that the approach to the problem will be easy. Notice if we include object B as part of the system, we actually don't care about the size of the force that object B exerts on object A, nor the distance over which that force is exerted. All we really need to find is the speed change for B. Now, of course, we can use the speed change for B anyway to find the work using the work energy theorem. But the idea is less calculation is better if you can do less, depending on exactly the nature of the problem. Now, of course, this is an important idea in general because the choice of the system ultimately affects the nature of the analysis that you'll do, but it's particularly important for problems where there's gravitational potential energy. Because one of the important things about gravitational potential energy, specifically for the AP course, because they ask a lot of questions about this in the multiple choice, is that an object on its own cannot have gravitational potential energy. Like a brick can't have gravitational potential energy. Gravitational potential energy can only be included as part of a system if the Earth is part of that system. Because the gravitational potential energy that we usually refer to as being experienced by an object or possessed by an object arises out of the gravitational force, which is an interaction between two objects. Once again, the exact same thing will happen. It's just that the method of analysis is going to be slightly different. If we take the example of just like a brick being some height above the surface of the Earth, if we consider this brick here by itself, where the Earth is not part of the system, then the force of gravity would be considered to be an external force. That external force would do external work, but since that force of gravity is going to act in the same direction as the displacement, that work will be positive and it will increase the energy of the brick. Of course, that increase in energy is going to manifest itself as kinetic energy because the brick is going to start to accelerate as it reaches the ground. On the other hand, if we consider the Earth to be part of the system, so now it's not just the system consisting of the brick, but the brick-Earth system, then the system has gravitational potential energy. And because the Earth is part of the system, the force of gravity that is exerted on the brick has an equal and opposite reaction force of gravity that acts on the Earth. So the net force, and thus the net work, would be zero. The idea then is that the gravitational potential energy of the object is going to change because of the force of gravity acting on it. But since that force of gravity is internal to the system, there is no net work done on the system. And as the system loses gravitational potential energy, it's going to gain kinetic energy. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at some problems. Okay, so here's our first problem. I'm going to walk you through this one and then give you some to solve on your own. This problem says a student knocks a plant off of a windowsill while watering it at a height of 5.27 meters off the ground. The problem says to use conservation of mechanical energy to determine the speed when it hits the ground. So the first question we want to address, you never need to write this down, by the way, it's just something you need to think about when you're solving these problems, is you need to consider what is being included as part of the system. The plant and pot, we're assuming this is a potted plant, is part of the system. And the Earth is part of the system. Notice here, it should make sense that the Earth is going to be included as part of the system so we can talk about the gravitational potential energy. But in this particular situation, we really have no choice because we are not given any information about the mass of this plant. And so we are, at this point, incapable of figuring out the external force of gravity that would be exerted on the plant system on its own. And so for this particular problem, the system we are going to be analyzing here is the plant system along with the Earth, so the plant-Earth system. And so this is what we have here. Obviously, the Earth is going to exert a gravitational force downward on the pot with the plant in it. There we go. And the plant is going to exert an upward gravitational force on the Earth. Of course, according to Newton's third law, those have to be equal and opposite. There is no net work done on the system, though, because in the system, these forces are internal, so there's no work done by any external force. Of course, as the convention table on the reference table says, those list of conventions, unless they specifically tell you there's air resistance, we assume that there's not. And so in this particular situation, we assume there is no air resistance acting. So how do you solve this problem? Well, the first thing you're going to want to do is write down the knowns. And so they tell us here that this plant has a height change of 5.27 meters. So it's going to start at a height of 5.27, and then it's going to go down to the ground. Because energy is a scalar, we don't need to make this negative. Yes, it is losing height, it is losing gravitational potential energy, but we don't really care about that at this instance. We also know that this plant, because it's just sitting on the ledge before it's knocked off, that the initial velocity of the plant is 0, and we know g, of course, is 9.8 meters per second squared. And we want to find the final velocity of this plant. So the first thing that we need to do here is we need to make our basic statement of conservation of energy. Essentially, this is the part where you just say initial equals final. But I don't want you to waste time simply writing that, E initial equals E final, because that's not really useful to us in solving the problem at all. It's true, but it's not really going to help us solve the problem. What I want you to do is basically do that, but not so generalized by just saying energy is energy, but talk about the type of energy present in the system in the beginning and the type of energy present in the system at the end. So what we have here in the beginning, because the object is up in the air at a certain height above the ground and not moving, is just gravitational potential energy. So we'll write UG naught, the initial gravitational potential energy, and then that's going to be equal to the final kinetic energy. We know that's equal to the final kinetic energy because the object is going to be down at the ground when we are considering it to be in its final state. So it's going to have no height above the surface of the Earth, and it's going to be moving. And so it has kinetic energy, and because it has no height, all of its gravitational potential energy is gone because it has been converted to kinetic energy. So this is your first move whenever you are writing the solution to any of these problems. You state what kind of energy you have in the beginning, what kind of energy you have at the end, and you set it equal to each other. After this, it's really just algebra. You write the equation for each type of energy. So we have mg delta y is our equation for gravitational potential energy, and we'll put 1/2 mv squared for the kinetic energy. Now, an important thing to realize here in this particular problem is that we were not given the mass of the plant. And they did not give us the mass of the plant because we did not need it, because now that we have a mass on both sides of the equation, we just get rid of it. And so to solve this for v here, and I'll put v final because it is final kinetic energy, so it will be the object's final velocity. To solve this for v here, we just need to multiply both sides by 2 and take the square root. So we get v final equals the square root of 2g delta y. And now all we have to do is plug in here. We have 2 times g, 9.8 meters per second squared. So it's going to be 20-ish. And then multiplied by 5.27. That's our height change. And so 20 times 5 is about 100. So this answer is going to be about 10. And of course, when you plug all those numbers into your calculator and you get an actual answer here, the answer works out to be 10.1 meters per second. And that's really it for this one. All of the gravitational potential energy that was possessed by this object in the beginning has turned into kinetic energy. And so we have a final speed of 10.1. Now, actually, that number on the calculator comes out to 10.16. So let's go ahead and call that. Let me just write in the 16. We'll do this. 10.16 meters per second, which will round to 3 significant figures because the height was given to 3 sig figs, I guess, as 10.2 meters per second. Fix it like that. Take a second to pause this video here and write that down if you did not get a chance to write down any part of the solution. And when you hit play, we'll take a look at another problem that I want you to try on your own. Okay. So here's another problem. This one says a baseball is hit almost straight into the air with a speed of 25 meters per second. Use conservation of mechanical energy to determine the maximum height reached by the baseball. Now, before I leave you to do this one on your own, it's important to realize here once again, once the baseball reaches its speed of 25 meters per second, the system that we are considering here is the system of the ball and the earth. So we'll call it the ball-earth system. Take a second to pause this video here and work out the solution to this problem. And when you hit play, we'll go over it. Okay, so in your list of knowns here, you should have the initial velocity of the baseball, which is given as 25 meters per second, the final velocity of the baseball, which is 0, because it will stop when it gets to its maximum height, g, which is 9.8 meters per second squared, and of course we are looking for the height, which we'll call delta y. Now, the basic statement of conservation of energy here is going to be that the initial kinetic energy possessed by the baseball, because it was moving and there was no height above the surface of the Earth, is equal to the final gravitational potential energy possessed by the ball-Earth system. Now, of course, we can say in the beginning, too, the kinetic energy of the ball-Earth system, where, of course, the Earth is stationary in our reference frame, so it doesn't contribute anything to the kinetic energy of the ball-Earth system. But that's the idea. And so now here, again, we just plug in our equations for the variables here. We have 1/2 mv naught squared equals mg delta y. Of course, the masses cancel because we don't need to know it. And we get delta y equals v naught squared over 2g. If you solve this as 1/2 v naught squared over g, it's important to realize that's the same thing. And so we have delta y equals 25 meters per second, whole thing squared, over 2 times 9.8 meters per second squared. And when you do that math, 25 squared, 625 over 19.6, you get 31.89 meters, or to 2 sig figs, 32 meters. And that's it for this one. Now, it might seem kind of weird that so far we have been using this for problems that you already knew how to solve another way. But it's important to realize at this point that, yes, we are going to be sort of dipping our toe into the ideas of conservation of energy by looking at problems that are more familiar. But the real power of conservation of energy is that we can actually use it to solve a ton of problems that we would be unable to solve by using kinematics or dynamics. And that's the real power of it. Not only can it be used to solve examples, which we could already solve another way, but that we can actually use it to solve new examples that we've never seen before and that we would be unable to solve using kinematics and dynamics. It's important to realize actually that this exact problem is a problem you've already had before. We talked about this when we were doing object thrown straight up in the air problems. And here you were asked to calculate the maximum height, and we did. This was the slide where I showed the solution. Notice here, the structure of the time-independent equation has you taking the square of the initial velocity and then dividing it by 2 times 9.8 meters per second squared. And when we use conservation of energy, we take the square of the initial velocity and we multiply it, or we divide it by 2 times the gravitational acceleration. Same structure. The only difference really is that we're not worrying about the signs because energy is a scalar. Similarly, this problem we actually solved using a fairly familiar looking equation, or at least it should be fairly familiar looking, because if I asked you to solve this on the free fall test, I said this object falls 5.27 meters, what's its final speed? You probably would have used the time independent equation. And you would have said the initial velocity is 0 here, so the final velocity is 2a delta x. Notice the structure of this equation is exactly the same. We're taking 2 times the gravitational acceleration times the displacement experienced by the object. Of course, the only difference is in the free fall test, you would have made both of these negative because they're down. Here, because energy is a scalar, we don't worry about that. So it's important to realize we can at least right off the bat say for sure there's something to this idea, to conservation of mechanical energy, because it's giving us the same answers that kinematics would. And that's an important feature of any, physical law, that it gives us answers we already knew would be the answer. And now we'll see the real power of it next week when we sort of take this into new territory, essentially. All right, before we wrap things up for today, I just want to take a look at one more problem. And this is probably the most difficult one we're going to look at for today. But it's definitely an important kind of problem, and definitely a problem they could ask on the AP test, or at least of a similar style. It says here, a baseball is thrown almost straight up at a speed of 12.3 meters per second and falls back on the roof of a building 5.42 meters above the height from which it was thrown. It says here to calculate the speed of the baseball just before striking the roof. So we have the object on the ground. It's launched up with a speed of 12.3 meters per second. It goes up to its maximum height. And I'm just sort of stretching this out a little bit to make it not right on top of each other. And then it comes back down and lands on the roof of a building, which is 5.42 meters above the ground. The question here is calculate the speed of the baseball just before striking the roof. Now, I want you to take this in stages because I don't want you to totally waste your time here by doing this incorrectly. I want you to take a second to pause this video here and just write down the list of knowns and the basic statement of conservation of energy. And then when you hit play, we'll go over that and then solve the rest of the problem. Okay, so here they tell you that the initial velocity of the baseball is 12.3 meters per second. They tell you that the change in height of this roof here, as you can see in the problem, is 5.42 meters. We know here that G obviously is 9.8 meters per second squared, and we're looking for the final velocity of the baseball. Now, there are a lot of ways that you can do this problem, and a lot of you, when we were doing these kinds of problems on the free fall or object thrown straight up in the air test, a lot of you sort of like took a long cut, if you will. You simplified the problem by using the maximum height, which actually ended up making the solution to the problem longer. Here, it's important to realize conservation of energy rather simply allows you to just do this in one shot. And the way it allows you to do this quickly here in one shot is by just making your basic energy statement. In the beginning, the object is on the ground and it's moving, and it only has kinetic energy. At the end, however, the object is on the roof, some height above the ground, so it has potential energy at the end, gravitational potential energy, but it's also still going to be moving because it's not all the way back down to the ground and it's not at the maximum height. It's still moving. And so it has kinetic energy here at the end as well. So the basic energy statement here is that the initial kinetic energy is equal to the final gravitational potential energy plus the final kinetic energy. And using this equation, you should be able to go ahead and calculate the final velocity in one move. And I'd like you to go ahead and do that now. Take a second to pause this video here and write out the equation, the full energy statement for this situation, solve it for the final velocity, and when you hit play, we'll go over it. Okay, so your conservation of energy statement fleshed out a little bit should look like this. Your initial kinetic energy here is 1/2 mv naught squared. Gravitational potential energy here is mg delta y. And the final kinetic energy here is 1/2 mv final squared. That, of course, is what we're solving for. Now, the first thing to pay attention to, I think, is that every single term in this equation has an m for mass. So we can just get rid of that straight away. Cancel out the masses. What we have is 1/2 v naught squared equals g delta y plus 1/2 v final squared. To solve that for the final velocity, you have a number of options. The form that you can write this in really depends on how exactly you want to look at it. But it should be clear that the first move is going to be to subtract g delta y to the other side. Since we're solving for v final, I'm actually going to move this to the left-hand side of the equation, though. So I'll have 1/2 v final equals 1/2 v naught squared minus g delta y. So I have 1/2 v final squared equals 1/2 v initial squared minus g delta y. Now I have to multiply both sides by 2. So I have v final, and I'm not going to write the squared because eventually I'm going to take the square root. But when you multiply 2 here, you just get v naught squared. And then you have minus 2g delta y. And of course, because this v final was squared, I want to take the square root here, and that's my final equation. So plugging into this equation here, I have the initial velocity squared, 12.3 meters per second, whole thing squared, minus 2 times g, 9.8 meters per second squared, times delta y, 5.42 meters. And when you do that math, plugging all those numbers into the calculator, you end up getting a final answer of 6.71 meters per second. And that's it. Now, the key detail here should be fairly straightforward. Number one, it is perfectly reasonable to expect that the final speed is going to be less than the initial speed because it has not gained all of that kinetic energy back. Basically, some of the initial kinetic energy possessed by the ball is sort of locked up in the gravitational potential energy. And because it's now stored as gravitational potential energy, it's not able to be used as kinetic energy. And so we would expect our answer to be smaller. And it's important to realize that that's essentially what the structure of this equation says. We've canceled out the mass, so we don't need to worry about that part. But basically what it's saying is the final kinetic energy here, or the final speed, is equal to the initial speed's contribution to the initial kinetic energy minus the part of it that's being used by the gravitational potential energy. And so I think the structure of that equation then really makes sense. But with that, that's it for today. If you have any questions, obviously, please let me know by email or message. And enjoy the 3-day weekend, everybody. Take care.